The homework, let's see, we got a couple of minutes, but the homework seemed to be fine, like everyone did well, except one group got 78, which they didn't, I think they didn't answer some of the questions, so that was, right, for undergrad, 78's like a high B, I guess. For the grads, isn't good, but so this thing, the tacticity thing, like if you, so you shouldn't use the word direction in it, like pointing up, down, left, right, direction to talk about tacticity, because the along the carbon-carbon bond, it can spin around. So there's no direction to it, right? There was a side group sticking off and it can spin around as many times as it wants. It can be up, down, left, right, whatever. But so you have to say, the best way to do is just to define with the Newman projection, the M and R dyads, and then say like MM would be isotactic, MR is symbio, or RR is symbio, MR's or RM or hetero. And atactic's a random mix of those. So it'd be 50% hetero. So that's kind of like the best. It's almost like a set piece. And if you, it's also a set piece, like if you say pointing up or left or right, that it's automatically kind of like run. But I didn't take points off for that, but just to kind of keep in mind. I mean, and then I guess people missed this someplace. It says like describe the OPLS force field, but in kind of a weird way. So people just missed that. So
I think the question was so long.
Yeah.
What we were trying to answer is kind of buried within everything.
Yeah, anyway, I took 2 points off. But I gave you 2 points back somewhere. So probably got washed out. Because some people saw it and answered it. So it seemed, anyway, 2 points won't kill you, I guess. I agree. It's buried. When I look back at it, it's like kind of super buried and it isn't worded very well. It isn't worded as a question. So I think I should probably highlight the questions, other questions. But otherwise, everyone did pretty well on that. Some people did like great. Some people did okay, but everyone kind of did that. Oh, but the group that got the 78 didn't answer that one at all. I think there was a question they didn't answer. Then, so let's see. This thing, people, there were varied degrees of answers. Some were like great, and some were pretty good, and some were okay. So everyone did okay on that. Anyway, it's kind of complicated stuff. So I think it was pretty well done. It was did a good job. What else is in here? And then there were also varied. So basically, everyone kind of got a rough idea what's going on. It was good enough. So then some people did really well, and there isn't any. It's not anything to really point out. And there's any questions on that thing? Bear it. All right, good. So that's in the past. Let's see, so I want to go to this thing. So this is the last part of the of this kind of persistence like thing. And all right, so we have different kind of length scales in the small scale of the chains, right? Like the Kuhn length, and then this business about the resistance length changing with charges, polyelectrolytes. Anyway, so there's another side, and then in terms of dynamics, like once you get to a melt, melt a piece of polystyrene and you have a melt. So then the chains can entangle, right? So you have like the entanglement set up a network, and that network makes little pores that the polymer can kind of fit through. And those pores, so if you follow the path of a chain, it's surrounded by a pore that's made up of a mesh of entangled polymer chains. So that pore that it's in has a time dependence because the entanglements can relax. So it's kind of a moving pore, but at a time scale that's faster than the pore, then you can see the pore. Right, so that pore is called a tube. It was called tube by Edwards. And then DeGen's called it a tube too. So it's kind of there's a way to measure that with up somewhere in here. Well, you do a time dependent, I guess I don't have that right here. Here, oh, it's right here. All right. So that's the tube. That's from DeGen's book, the guy that won the Nobel Prize. So it shows like how the polymer can escape from the tube. So it's got a relaxation time to get out of the tube. And the tube itself also has a relaxation time. And the tube is made up of the same chain that's relaxing out of the tube. So it's a little bit of a complicated problem. But if you consider the tube's permanent, and you consider the chains reptating, they call it, out of the tube, which I guess has something to do with reptile. And it's kind of like reptiles move with this kind of squiggly way. You ever seen a reptile move? And then basically this thing's squiggling out of the tube. And it's got a certain time constant. So basically, if you take that time constant, you can predict this viscosity goes with a molecular weight to the 3/4 power. If when you get to the entangled regime. Right in the low molecular regime, viscosity is proportional to molecular weight. So it's linear. All of a sudden it shoots up, and if it's a power law, it's power 3.4. So this reptation thing actually predicts 3. If you allow the tube to relax, you get 3.4. So the combination of those two gives you the number that you observe experimentally. Anyway, so we'll talk more about that later on. But so that's another size scale, is this tube diameter. It's on the same, yeah.
Is this a theoretical tube, or are you actually growing polymers in that?
Nothing's growing. This is just it's a bunch of worms squiggling around. And there's a worm that's squiggling out. And you can think of the worm as squiggling, like freely squiggling, if it can follow the path of the other worms create. So within that thing, it's just diffusing like freely. But if it tries to go sideways, it's a dead end. So there's a cutoff size scale of the tube diameter with motion stops because it can't go that distance anymore. But with smaller size scales, it can go freely. So that's the idea. It's like a cutoff on the time. And when you measure this, you measure the dynamics of the chains moving, and you find out they stop at some size scale. And that's defined as this tube diameter. So you can measure it experimentally with something called quasi-elastic neutron scattering. So you tag the chain with deuterium and watch the time dependence of the scattering as a function of angle, and that gives you size, and you can figure out this tube size from that. And somewhere there's a picture of that experiment. And also that theory also predicts that diffusion coefficient should go with a molecular weight squared, which you can measure pretty easily. So you take this is just a profile where you tag chains with fluorescent, and then you watch how the fluorescent chain diffuses into the other one over time, spatial dependence, and the shape of that curve follows Fick's law, and you get the diffusion coefficient. Use different molecular weight chains, you can get this molecular weight dependence, this n squared thing, which is predicted by that same model. We'll talk about that model kind of quite a bit later on, but I thought as long as we're on looking at the small scale, there's all these other scales of things. This is that neutron measurement, and these are all different size scales, and the big size scales at the top where things don't relax, and things relax at the small size scale. So the cutoff between where it relaxes and where it doesn't is that tube diameter. There's no photograph of it, there's just that. There is a photograph because you can go to DNA. That's DNA, which is micron scale. So you can, and it's fluoresces, so you can watch the DNA go through a gel of other DNA or something. So you can, this is a kind of a verification that the thing, in other words, it starts out here and then it always follows the same path. In other words, that's the tube. So it's always following the same path. That's evidence of the tube. This is from, I think this is from, well, I don't remember. This is from a book. I don't remember which book. Anyway, the paper's given there, but so that's kind of a famous, you'll see that repeated, that photograph over and over. Same with this diffusion. These things are repeated a lot. And that's a computer simulation that shows I can see this tube, you know. So there is a tube. It's got a diameter, and basically that's a size scale on the same size scale as a Kuhn length. So we have the Kuhn length or the persistence length, which are related to each other. And then we have this tube diameter, And there's another thing called a packing length. So there's like 3 size scales. Both of these are for the polymer melt, like when it's in a solid state. So you have solid polystyrene, you melt it. That's the melt, right? So it's concentrated. Coulomb length, persistence length is the same across, no matter how you look at it, right? So anyway, so the Coulomb length is 1960s, I guess, and the tube diameter is 1990s, 80s and 90s, maybe 70s. And then the packing length is kind of the 2000s. So all these are still like 30 years old, but basically this is the newest of the group, right? And packing length is kind of an odd thing because the tube diameter, you can envision it. You know, I can draw a picture, you can do a computer simulation, you can observe it, and you can do the DNA thing and kind of see the tube. But in the persistence length, you can kind of see, I mean, you can measure it by looking at micrographs, for instance, and just do this calculation of the tangents to the line. So anyway, but the packing length you can't see. So the packing length is a completely kind of hypothetical thing. So of the 3, so it becomes more and more esoteric as you go down here, right? So basically the packing length grew out of this guy, Tom Winton at University of Chicago, I guess who's now retired, but was looking at this problem. So these are block copolymers. I mentioned that before. So you can have like styrene butadienes, that's SBR rubber. The styrene's glassy at room temperature, the rubber is rubbery. The glassy things cluster together. So they'll make like, say, spherical, is the butadiene's longer, it'll make little domains, spherical domains of styrene, which are glassy, and it'll link all these chains together. Say if it's a tri-block polymer, copolymer, right? So ABA, then all the polystyrene will be in these domains. So it makes a rubber that you can melt, because the polystyrene will melt at 120 C. So you can extrude it, and then you can make like a tire, basically. I mean, when they actually make tires, they do that. So there are styrene domains, but the butadiene has unsaturated double bonds, and then you put sulfur in, you can vulcanize it. So this part is actually chemically cross-linked, and this part is this physical cross-link. So you have kind of 2 kinds of cross-links in SBR rubber, basically a tire tread, you know. So anyway, with 60% carbon black, and it's mostly carbon black, and this rubber is like holding the carbon black together for a tire tread. So and it's got, well, it's got like 30% oil, so there isn't much rubber in it actually. If you take like half carbon black, 30% oil, you have like 20% of this block copolymer in a tire tread, right? So it's really a gel of the polymer in oil with a lot of carbon black in it. So I mean, that's kind of a weird thing. Think of it as like a single polymer molecule or something, that whole tire, because they're all cross-linked together, but actually it's just a gel. It's almost like a oleo gel or something, you know, like a hydrogel almost of oil and polymer, and then mostly carbon black. Anyway, so that's SBR, but so the idea is like, if you know the molecular weight of this chain, then what's the size of those domains that you form? Like that's kind of the fundamental question that came up in the 1990s, right? So, and if you look at this, so the bottom thing is like the ratio of the molecular weights between A and B. So that's pure A, that's pure B. And then as you go across, and this is the temperature, 1 over the temperature over here. So this is like a upper, so you're cooling it down as you go up. This is 1 over temperature. I'll explain that term in a minute. Anyways, you cool it down, it phase separates, but it phase separates into these nanoscale domain structures that are perfect. Like it makes perfect structures, right? So one thing you can do, you can swell one of the phases with water. Say you use PEO, you could swell it with water, and in that water you could put silica precursor like TiOS or SiCl4 or sodium silicate, things like that. So basically you could just swell that with a ceramic precursor, change the pH of it, make that red turn into glass, and then stick it in an oven and burn all the plastic away. And then you have a perfect porous ceramic, which can be used as like a catalyst support, right? So that's a way to make an artificial zeolite, because these things are going to be like 10 nanometer hole sizes, which could be perfect for filtration, nanofiltration or something, right? So this is industrial at this point, mass scale production of things like that using these templates. Anyway, so that's a map of it. So if they're equal, you get a lamellar structure in the middle, 50.5. As you go out, when one gets larger than the other, you get cylinders kind of for obvious reasons, like in order to pack it, one is longer, it has to make a cylinder. And when it gets really much longer, then it becomes a spheres at either end. So they're opposite phases, like this is mostly styrene, that's mostly butadiene. And this is a 50-50 mixture. Right, so that's kind of the mapping of these things. I mean, that's the theoretical mapping. This is kind of like actual mapping. So things get dicier, like if you go to real experiments in this. Oh, the Washington Post is giving me all kinds of notifications. It's so important. Like, but sometimes it's useful, I guess. Anyway, that shows how it might pack. It's just like the micelles. So these are polymer micelles, right? So, and then the lamellar one is the one that's easiest to calculate. So this is how you do it. So, all right, so let's see. This is where I got some notes here. Which I probably lost immediately. That's why I wanted to take this out. I just wanted to go through this thing. Here. So this is called a scaling, more or less a scaling argument, which you're going to get in polymers a lot. So it's not like a real mathematical picture of things. It's more like how things, like, so you want to get, for instance, so you have that, go that way. This guy, all right, that's interesting. All right, other tune, zoom out. Just keep those at the same time. That's happy. That's good. All right. So we have this thing, and we have, let's say, polystyrene and polybutadiene, right? And then there's this interfacial region. So you're saying first, if I have one chain, right, I'm going to say that one chain is going to look like this. They're equal, right? I have this distance dt, it's the thickness of that interface where the two chains meet. Somewhere in this is the chain, right? And then there's also this length, like what is the stacking period? So these are going to stack up like that. What is that DAB? So that's called DAB, even though it's polystyrene PDB. Right, and then at the interface between those is an area. So you say that the polymer is a cylinder like that. Right, so, and then you're going to define, so at this interface, there's kind of an energy penalty or an energy benefit, depending on if the things like to be together or don't like to be together. So you're talking about the energy, an energy balance in the same. So if they like to be together, that'll be a negative energy. If you drop energy, and things are good. And then it'll be a high energy if things are bad, like it wants to phase separate. Right? So you gotta have some kind of energy, call it an average energy. And then the way to get that is like the A1, and then minus what it is in the AB, right, would be the difference, like from going to pure A to in that interface is an energy penalty or there's an energy benefit. Right, so it would be penalty would be plus, benefit would be minus. So, and then you could also talk about the B ones going in. So plus BB minus another one of these. So there's two of those. Then you say it's going to be the average, so it's divided by 2. So that's like the average energy. So this business is kind of due to Flory, but basically he stole it from a guy named Hildebrandt from Netherlands from like 40 years before Flory. Right? So this thing's been around forever, this average energy. And then you say like each of these units is in a Cartesian thing, so it's got six of these EAAs on it. Like you have A in the middle, you could have an A here, you could have 6 of those, or however many you have. So you just call it Z. So you say the total energy is going to be Z times that delta E. And then if you want to make that unitless, you make it relative to KT, and that Flory called pi. Hildebrandt called that the Hildebrandt solubility parameter. Right, so Flory just lifted that idea, except that these things are put together in a chain. That's a difference. So some of your EAAs are kind of fixed in this because they're chain. But you have that chi thing. So then you want to know. So what we're trying to get is, so the solution is going to be DAB equals the molecular weight AB to the 2/3 power. And then divided by 3 Coulomb squared, this chi parameter, this energy, unitless energy thing, and then the thickness of the interface, dt, to the 1/3 power. So basically, what can you prove here? Well, I mean, you know the molecular weight, so you can show that, and you can measure this. I mean, you just see in a TEM, you can see the stacking, you can measure the height of the thing. You can you made the polymer, so you know the molecular weight. So you can get this 2/3 power. And the other thing you can measure is this chi, because this chi has some number divided by T. So chi is just the temperature. So we can get chi also. So we know the temperature, we can get chi, we can change the temperature and see how the DAB changes. We can do different polymers and see if there's a 2/3 power dependence between DAB and NAB, which there is, right? So that's the final equation you want to get through this energy balance. So the interface energy, the first thing is like the interface energy, which is like the, that sounds like a phone call. Right, so anyway, the interface energy is going to be like, the interface is going to be made up of these mixed match things. And then you want to remove the KT thing, so you have to multiply by KT, so chi KT. And then it's going to be the volume of it. So it's going to be like how many units are within that interface, which is going to be the volume of the interface, which is this area of the interface, times the thickness of the interface is dt, divided by the volume of the unit, whatever the unit is, this VC. That's it. That's an energy mixing energy penalty. So if that thing is negative, that's good. Then everything will want to crowd down to the, will want to pull it down. And then DAB should be smaller. If that thing's positive, no, if chi is positive, it's going to make it want to crush down. Chi is negative. Let's see, if chi is negative, it'll want to pull down. Chi is positive, it'll make it want to push apart. Right. So that's kind of how this works. Right. So negative is good, positive is bad. Generally, you're looking at positive for this. Like, in other words, it's usually bad for mixed things. They want to demix. So they want to phase separate. So anyway, so that's the energy due to this mixing thing. It's kind of the first thing. So there's actually, how many things over here? 4 or something. This is 4 things to do. That's the first thing. So, all right, so interesting in this is that the operation is going to depend on this area, like the interfacial area, which has to do with kind of how the chain, how much space does the chain need, like laterally, right? In other words, so this is something no one thought of before this problem came up, and this is where the packing factor comes in. Like no one's, so you're looking along the chain, you have to walk of it, you know the dimension of that, you know the step length, but no one's ever thought about, well, when you get into a melt, they have to all get crowded together, and there's got to be like some space there, right, for them to get in, to get together. It's like this area is the first time people like thought about packing chains together, and they needed to know that because they needed to know, in order to figure out what the stacking period is, you had to know how many chains were in the interfacial area between the phases, because that will determine like how the size of this thing. And so anyway, so there's some like defining terms involved in this. You have that the chain is an occupied volume made up of NAB units, and each unit has this VC, right? So that's the occupied volume of the chain, and that also equals the thickness, the size of the layer, like this entire DAB for the entire thing, times the area. Right, so the cross-sectional area times that gives you the volume of that thing. And notice there's no factors, it's just like a scaling relationship. And then the number of units times their packing volume, the volume that each unit occupies, gives you that relationship from which you can get that DAB equals this NAB BC over A. Right? And again, like A is kind of like the magic number that's been invented here to account for like this situation. And it turns out then this A becomes important to like all of polymers, like in terms of the melt behavior, the rheology, which is a thing I'm interested in. All right, so that's kind of like number two of this thing, right? So we have this mixing energy at the interface, we have that DAB, then opposing that mixing energy. So in order for the chains to move, you're considering that they're like tethered, so they're like kind of like tethered at that interface and they're tethered at the other end. And in between, you have your jump rope thing. So rubber elasticity. So that when the temperature goes up, that distance goes down. Right? Because the jump rope spins faster, it pulls on the ends of it. Right? And we know that function goes to from when we compared the Boltzmann to the probability for chain ends, we have this KT R squared for the energy in L squared. So when you take the derivative, that 2 goes away, and we have the modulus, or the string constant is 3 KT over NL. So 1 over N gives you the modulus of the retractile force goes with 1 over the molecular weight. And so that's the other force. So you're going to balance this mixing force with that force. So that force is going to be minus 3 over 2 KT, and then KT over, right, so let's see, KT R squared, let's see, how do we get that from? Squared, go. So R is DAB, this R is the DAB here. So you say R squared, then you have NA, the number NAB squared, and then BC squared. That's R squared. Because you said what DAB was in 2, which is R. R is DAB. R is the length of a chain. And you get a scale, it's like 2 or 1, doesn't matter. And then the NL squared part is N is NAB. And then L squared is LK squared. Oh, and DAB has an area squared too down here, area squared. So you have NAB cancels out. Then you have this other energy that's minus, because it's a retractile force due to temperature. So as the temperature goes up, it's going to pull in. So you have minus 3, 2, and KT minus N squared, E squared, divided by LK squared, and then area squared. Right. So this is the other energy. That's the retractile energy. That's bad. Change the world here. Right. So you just equate those two energies, like the two energies. Right? I mean, you don't equate them. You sum them up. So you have the total energy, and they both have a KT prefactor, like KT and KT. So you can just say delta G over KT, the free energy for the chain is going to equal the chi thing, the energy thing, and then A dt, and then VC minus 3/2 M VC squared, and then LK squared minus area squared. And then you say, so this is where Tom Whitten, this is where the packing thing comes in. He says, this is why it's so important to know that. He says, he's not going to minimize the D, like he's going to minimize the A. He's going to figure out like he's going to minimize it to A for whatever reason. I mean, it's not exactly logical, except he gets the right answer. Like, why would you, anyway, he's minimizing against A. So he's going to say, so to minimize it, say the derivative of that delta G by KT A equals 0, right? And that's going to give me the answer for that function. Right? In other words, this term, the A drops out, you just get chi dt over VC. In this term, the 2's cancel, and you get 3 n to the LK squared LK squared raised to 3. Let's see, let me do this. A cubed, I guess. A cubed, and then because it's minus, that becomes plus, and the 2 goes away. Yeah, so anyway, that equals 0, and then you solve for A from that. You find out that A equals 3, and the volume of the unit cubed by LK cubed, K squared chi dt, the thickness of the interface, that whole thing to the 1/3, because A was cubed here. And then then you go back to the equation, the first equation, number one, dA is M dC over A. So the thickness thing that you wanted, and if you plug in that A, then you get this equation, the original equation. A little tedious, but basically it's just an energy balance. The energy, you sum the energies, and then you take the derivative with respect to A. So the whole thing is based on this kind of idea of the interface packing of the thing is like the concept that's important. And from that, so that, I mean, for one, it's important to know about block copolymers, and that's kind of like the seminal thing for it, you know, to see it. And then anyway, so out of this comes the idea that A is important, and then Witten came out with this concept of a packing length, but
When you say A, that was the,
cross-sectional area of that cylinder.
okay,
Yeah.
the derivative of that, yeah.
So you take the derivative of the free energy with respect to A. She's saying you're going to minimize the energy by changing A, meaning you're going to change the packing of the chains. So you're, in order to make the size, so you take the cylinder and you squeeze it, then it's going to make it get longer, or if you let it go wider, and you're going to let it squeeze or go wider, you're going to find the minimum. In other words, oh, it gets hard to squeeze, and then you pull it out and you find, oh, it's hard to pull it out. And right in the middle, there's a place where it's a sweet spot. So derivative of the free energy with respect to A, that's the sweet spot for A. That determines, because it's like a balloon, it's got to go up and down. You know, so that determines the size. That's not an obvious thing to do, right? I mean, you would just take the derivative with respect to the size, but that doesn't work because you still end up with A in it. You know, so basically, this way it works using the size, the length itself. I guess it didn't work. This is how they did it anyway. So, and again, like, I'm sure that they knew the answer before they did this derivative. And they worked back to figure out how to do it. You know, because it isn't just something, I don't think you'd come up with this, that minimizing with A.
Yeah.
That isn't, anyway, in doing that though, then it was like a Yahoo moment or whatever, you know, because he said like, oh, there's a different size. Like there's another size that no one's even ever looked at, you know, it's like the size that these things have to fit together. And then, well, why is that? Well, then, all right, so at the time he was working at Exxon Central Research in Annandale, New Jersey, which is right on the road to Newark from whatever, Allentown or whatever, you know, right across the border. Anyway, and then he also, so they pay a lot of money. That's like that. It's a small place. I think they only have like maybe, I don't know, maybe like a maximum of 1,000 people work there. But basically all the geniuses of like polymers and catalysts, like they have a whole section just for all the catalyst geniuses, and the polymer guys are in another place. They mix together. It's like it was like the Bell Labs kind of, except in a compact form. It's still there. I mean, so and unlimited resources. Like they own synchrotrons and stuff, you know, neutrons and synchrotrons, they own that stuff. So basically anything you wanted there, like Exxon had plenty of money, you know, it was not a problem. So a lot of people flocked there. And a lot of the big universities kind of wanted to get in on it too. So it's like, and the biggest, I don't know, I was looking at the cost of universities, so what is it? $85,000 a year to go to University of Chicago, which is where Witten is, or was. That's the highest in the US. And like Chicago, Northwestern and University of Chicago are like tied for the highest. You know, so it's kind of like, if you're complaining about tuition at UC, you know, it's like, it was something that anyway, so it came up because people were complaining about $40,000 tuitions. It's like, that's nothing, you know, it's like half price, you know. So anyway, so not that any of us can afford that, but so anyway, yeah, so if you take that packing number, it turns out you can predict the so he calls it A, and Witten called it A. Later on, Loshi, who's at Exxon Central Research, and there's a synthetic guy. What's the other guy's name? There's another guy that's at Cornell now. Was it Exxon Central Research, but they call it P. So it's a packing factor, they call it. That this reflects how the chains kind of pack together. So basically you can predict this plateau module through the storage modulus versus frequency. This is where the entanglements happen, and it's a constant, you get a constant modulus. If you take that elasticity modulus, so you take our it was 3/2 3/2 NL squared, so ME is replaces N. So you take the molecular weight between the entanglements, and then you get an elasticity for the change between entanglements. So it's like a cross-link system at that time scale with the entanglement serving as the, so you get a flat plateau modulus. It's a characteristic of the material. You can predict it with this packing factor. And then you can predict everything from that. They can predict all the plateau moduluses of everything in the world using that packing factor and the Kuhn length. Right, so it's an important number, but it's not exactly something you can draw a picture of, right? Or you're not going to see it in a microscope. Like you're not going to have a TEM. You can get a TEM, you can measure the Kuhn length. You can't get a TEM and measure this packing length, right? So
Are there any assumptions within that formula for that modulus from the previous page?
yeah, it's assuming a Gaussian chain. So remember, our original thing was a Gaussian chain. We use that exponential function, and then you compare it with Boltzmann, and then you get the energy, you take the derivative, you get that spring constant. So that's a rubber elasticity equation, right? And it's equally useful for predicting this plateau modulus. So you'll see that, when you see that all over, so you should kind of, that's like a warm spot, you know, when you see this elasticity equation, this equation, so the size squared times KT 3/2 NL squared, that's like a fundamental equation repeated over and over again. So people just pull that out of their hat. So like here, and then plop it in there, right? It assumes a Gaussian chain. If it's in solution, the chains aren't Gaussian. So we'll talk about that next, but basically in a melt, it's a good bet. Like that's going to work. And it's been demonstrated like over and over and over again, you know, for every, like, even if you take a rubber, put it into solvent, and then it'll swell. So basically predict how much it'll swell from that same thing, because you're stretching out the chains, and if you use that modulus, you can say how much it'll swell. You balance, in that case, you balance the chi thing and mixing with the elasticity, and it gives you how much it swells, basically the size that it would swell to. So that equation is used like every place. Like every time you want to think about chains doing anything, that's the first thing that tells you the elastic response of the chain. Right. So it's a good thing to kind of notice, I guess. I think you get familiar with it if you see enough things where people use it. But anyway, so it's used here too. I mean, it's basically that this is like the bag of tricks, and that's the number one. It's like if you want to label them A, B, C, D, it's like B. Like NL squared would be A. This would be B. You know, I mean, sometimes it's good to label things. Then you can say, oh, equation B. You know, that's, and then basically Polymer's equation B. So anyway, so that's the packing length. I mean, there's various ways to describe it. So the idea is, so the packing length can be the occupied volume by R squared, mean R squared, or NL squared, or it can be related back to the spring constant. You know, so you can, so that's what Loshi, let's see, Milner is the guy at NIST, Wang, I don't know. But basically, Loshi is probably cited here somewhere. So all these, Milner, that's a Milner thing. That's for the block copolymer. So Dave Loshi is retired now, but he's like one of the guys that did this. And then I don't see the chemist guy here, which I forget his name. One of these papers is him. This is from a Loshi paper. Who is this? Colby. That's just our guy. But so anyway, so I'll remember his name in a minute. Anyway, so basically that's another number. So we have like these numbers to look at in terms of small size scale, which is, so this isn't short range interaction. This is short range interaction, Kuhn length, persistence length, and then tube diameter is kind of dynamics on the same size scale. So you see Kuhn length and tube diameter might be almost the same number, right? And then packing length is another thing. So these three things are independent of each other, but they're all around the same size scale. So you can observe Kuhn length. Tube diameter, you can kind of observe. And then packing length is just a hypothetical in a sense. It's basically the elastic modulus, but in units of length. Right? So plateau modulus. Anyway, so that's that. that kind of ends this, and that goes like summary, here. So, yeah, so the next thing is this, like to look at, any questions on that stuff, or,
relationships. Will they develop like experimentally?
well, yeah, I mean, almost always, yeah, people had a really good hunch of how it was gonna behave. And then yeah, I mean, almost all of them are derived, I'd say every equation you have was derived from an experiment and then working backwards. I think there are none that were derived otherwise, but maybe there's some, but I don't think. The idea that some guy's sitting around smoking a pipe and then he's just gonna come up with this thing out of the blue, that doesn't exist, I don't think. I think all of them, if you look at it, but always they'll be presented like, I was sitting around and I had this idea. So they'll always present it that way because they want you to go, gee whiz, But basically, that's not how things work. So don't say gee whiz much. Say like, kind of look at it carefully and see like what he did, because then you can see like, oh, he made up that part. Like that part just came out of the blue and it has no basis. But if you look at it from the beginning to the end, it's like, it kind of makes sense, and you just skip over that part. But if you look at it like he had that answer, then he had to make a thing that fit that. Then you can more easily see where they cheated. And that's where you find out that Mendel made up the numbers, because he knew there was genetics. You could see it, group P's. Then so he just had to prove that there were genetics. So I think everybody works that way. That's kind of a real scientific method. There isn't any kind of idea like you're going to do this. Oh, I have a hypothesis. It came out of the blue from nowhere. Then I'm just going to go test it. Oh yeah, it's right. So it's kind of like, it's a myth, It's like Santa Claus or something. So anyway, so it's the Santa Claus of science. All right, so let's see. Anyway, so we got that. All right, that's the way I think. You might think differently, but you're wrong. Anyway, so anyway, so the next thing was on that other slide. But anyway, all right, where is that other slide again that I just got rid of? There. So we got this issue, like the chain. So you can put it into all right. So there are solvents. So you can put the polymer chain into a melt. It's got a certain size. If you put it into a solvent, it generally gets larger, right? It's got a larger size. And then if you put it into a bad solvent, it will collapse down. So if you have a dilute condition, say you have polymers in a dilute solution, and then you put them into a poor solvent, they'll collapse independently as coils. But so this is basically protein folding. Like going from that to that is protein folding in a nutshell, right? Because they still have polar groups on the surface, so they're still like a colloid floating around and it still stays suspended. It's a colloidal suspension. Then this is a polymer in solution. This is a polymer in solution. So if you go between those, you can change the solvent quality with the temperature. It'll precipitate out if you lower the temperature, right? So you can find a temperature where it just matches what it would be in the melt. So that's called a theta condition, right? So this is kind of known that this can happen, that the coils are larger when they get into. Then finally, if you have like a polyelectrolyte with charges on it, you can fully extend the chain. It can be just a rod, right? Contour length chain, right? So you can go, actually there's 4 ways to be, right? 4 kind of classes of ways to be. Totally fully extended, where the persistence length is larger than the chain. Then this good solvent where it's swollen, theta solvent where it matches the melt, and then this kind of protein folding state, denatured or natured, whatever, native state protein. Right. So anyway, so we've looked entirely at this thing, right, so far. But if you take a polymer and throw it into toluene or something, this is the thing you have. You don't have that, right? So the idea is that also when we did the random walk, like the chain goes along randomly, so diffusion path, it doesn't matter if it diffused there before, it can cross it, right? But in this case, this is called an excluded chain. So basically, or expanded coil. So It's basically the chain goes along and it finds that it's going to cross itself, it doesn't do it. So that means it has to be larger because it has to find more space to fit in to not do the things where it would have crossed itself. So those are, again, those are like long range interactions. So the chains go on, and it doesn't even know where it came from, and all of a sudden comes up against a wall and it has to go somewhere else. Right. So that's a long range in terms of along the contour length. It's a long distance between one unit and another one. In terms of distance, it's the same distance as the persistence length. Yeah.
Did that have to do with the like self-avoiding walk?
Yeah, this is the self-avoiding walk.
Okay.
Yeah. SAW. Yeah. And this is a random walk. Right. So depending on what field you're in, they call it different things. Basically, this is an expanded coil. Anyway, so first thing is like to get that, and Flory did that. And Flory and Krigbaum did that. So Krigbaum, I was going to look that up, but basically Krigbaum was, I think he was Flory's postdoc. So Flory was at Ohio State, got his PhD, came to UC, taught in chemistry, an old chemistry, which is being torn down now. And then I think he went to Goodyear to work for a while. And then and that's where he developed Flory, that chi parameter business. And then he went to DuPont. A guy named Carruthers was there. He was a guy who invented all the condensation polymers like PET, polyesters. So Carruthers was a genius. He would have won the Nobel Prize, but he killed himself. He made his own cyanide and killed himself for some reason. I think he had a love life problem or something. But anyway, he died. And then Flory at that point left DuPont. He was already really famous and went to Cornell. And then I think when he was at Cornell, Krigbaum kind of hooked up with them, and then they, not hooked up, but he got together with them, and then they came up with the Flory-Krigbaum theory. And Krigbaum went to Duke after that, I think. This is in my mind, the chronology. And then June Rowe, who was a faculty here, was at Bell Labs at the time. Or June Rowe went to work with Krigbaum. He got his PhD with him at Duke. And then he went to Bell Labs. And then Rowe came here. So Rowe was a direct descendant of Krigbaum. Krigbaum is somehow linked to Flory. There's a couple of links with UC between this Flory-Krigbaum theory, even though Rowe didn't do anything with Flory-Krigbaum, but he did stuff like orientation of crystals and stuff, polyethylene crystals. So anyway, let's see. So yeah, this is a nice little thing that came out. So first off, yeah, we have to go through this business first. So anyway, this is a kind of a thermo review you probably never saw or whatever. But anyway, ideal gas, PV, PVs and RT. So say P RT over V. Or if you say, if it's actual volume, if it's molar volume, then you get rid of the N. So it's P RT over V if it's molar volume. Right. So anyway, so van der Waals said, well, things can hit each other. So the same problem, like excluded volume. So none of this stuff was new by the time Flory-Krigbaum came up upon it. Right, excluded volume existed since the 1880s, I guess. Van der Waals, right? So anyway, the idea is like there's a volume, but the volume is less because you have this exclusion of the thing actually is there. Right. So the balls, spheres, whatever, hit each other, and that's the excluded volume. So I think it's like 8 times the volume of the sphere somehow if you figure out in 3D space what's excluded. Then anyway, so there's an excluded volume idea, and that what that does is it increases the pressure because it can't. So the particles are flying around, hitting the wall, making pressure. But if they can't go through each other, then you get more hitting of the walls, you get more pressure. That's the idea. So this B excluded volume has to increase the pressure. So if you have a system, if you're using this to model, like if things are going to phase separate, that will make things stay in solution better. Like the excluded volume makes them dissolve better, the things, okay, because the pressure goes up. So anyway, so if you want things to phase separate out, you need an attractive potential between the spheres, and then they would have competing against this Brownian motion, and then they would attract and precipitate out into 2 phases. Right, so you need to have an attractive potential to make this happen. So that would lower the pressure because it's going to make, when the things cluster together, they don't hit the walls as much, you have a lower pressure, right? So you have this attractive potential, right? So you end up with these like 2 terms, excluded volume and attractive potential. So excluded volumes are random walk, is our random walk thing. Like it's going to make the coil expand, self-avoiding walk. I mean, not random, but self-avoiding walk. Then this thing's going to allow us to have a temperature dependence to it. In other words, this thing will allow us to have a phase separation in the system, right? Because this term should be temperature dependent. It's got T in it. This term isn't temperature dependent. So if temperature changes, there's regions where this term will overcome that term. In other words, you can equate these two terms and find out what the magic temperature is. Like when those two terms equal 0, that's like a phase separation point. That's a critical point for the system. Because this one has temperature, that one doesn't. Just solve for temperature in this, and you get the magic temperature, where if you cool it down below that, it phase separates. Right, so it's a nice little ditty that he did. And this is if you straighten this out in terms of volume, you end up with a cubic equation. Like if you multiply by volume, then you end up with volume cubed out of this thing. So this is a cubic equation of state. It's the first one. Right? So that means that you can solve with a cubic equation of state, you can solve for phase separation. Anyway, so I mentioned this is because Flory had done his PhD in physical chemistry. So this was like ingrained into him, right? And Krigbaum too. So they knew like exactly all about this stuff. And they were thinking along these lines when they developed their thing, right? So anyway, so if you take that equation of state and then you compare it with the viral expansion. So if you take the compressibility factor and expand it in density, so it would be 1 over n over volume, right? So you can get, like the first term would be the ideal gas law, that equals 1. So P over PV over RT, so rho is 1 over specific volume. That would equal 1. So Z would be 1 for an ideal gas. So that's the lead term. And the second term would be expansion in density. So the first one's called the second viral coefficient. So that's another way to talk about pressure. So if you equate those two pressures, solve for B, you find out that this B, this second viral coefficient. So first viral coefficient's 1, the second is this number, is like the excluded volume minus this attractive potential for the beads to stick together. So basically, this B2 is excluded volume modified by this attraction. So they're gonna repel each other with a hard core, and then they're also going to attract some, and those two things can balance out. So this is ideal gas. This is non-ideal gas with excluded volume and attraction. And this ideal gas number can disappear when you have the magic temperature. So when this thing equals 0, it's like B over A becomes like the magic temperature. No, excluded volume over this A term, whatever that is here. This thing, T star is A over RB, right? So this is B over A. But, so anyway, so this was known in 1850. The reason I'm mentioning this is almost exactly what Florian Krigbaum did. So it's important to give context to it, right? So not say, oh, out of the blue, they came up with this idea. Well, they had all this framework is exactly the same thing, but they've changed the names to protect the innocent kind of thing. To kind of confuse it and then to present it from the beginning like we invented this thing. Not that it isn't a genius thing that they did with this, but basically it's pretty important to kind of keep a context to it. Anyway, so this is how they did it. So they had the probability of an end-to-end distance is that, and if you equate that with the Boltzmann, you can say there's an energy for a chain, right? So then they're talking about probabilities for chain positions, right? No, it's chain end-to-end distances for chains. That's the topic. So they have like the probability for an end-to-end distance R is that thing. This is a Gaussian function. And they equate it with Boltzmann, they can get the energy of a chain from that. Right. So they kind of want to get the energy of this excluded chain. So they say, what's the probability of excluding a chain? Right. So you say 100% minus the volume of 1 unit of the chain. In other words, what's probably going to run into a unit of the chain? Well, 100% minus, the probability you're not going to run into another unit of the chain is like 100% minus the volume of the unit divided by the chain volume, which is R cubed. So that would give you the probability of not running into another unit of the chain, which is a high. R is a huge number, right? It's going to be on the order of like 100.1 micron. And then this thing is going to be a really small number, like 0.1 micron. So it's going to be like 1,000, 1 by 1,000, this number, right? So So this thing's gonna be 0.9999999 whatever. So it's gonna be unlikely you walk into another chain, but you have n, this n times n minus one over 2 factorial possibilities of two things hitting each other. Like the probability, like the roll the dice thing, right? So you have, so if you take the probability of one and the probability of that many, you have to raise it to the power, probabilities multiply. Right, so you raise it to that power, then you have this messy thing. It doesn't look anything like that, the original energy thing, right? So, but they figured out that you could mess around with this. Like if you take the log of this, the power comes out front. So you take the log of that, the power comes out front. And then you take the exponential of the log and you get the same thing. Like exponential log are reversing functions, right? And then you can use this thing like exponential, numerical expansion exponential is 1 plus x squared over 2 factorial plus whatever, right? So take the first two terms of that, take the log of that, so you have 1 minus, but it could be plus. So ln of that would give you x, right? So 1 minus x would give you, so if you take just the first two terms of that, this log of that thing becomes just that minus that thing. So minus n squared VC over r cubed 2, which is of the same form as this guy, right? So you can just plug it in. So you can say, this is already minus, so you have the energy was this, so you're just going to add that term to it, the n squared VC. That's the energy of the self-avoiding walk chain. Like it's just a little ditty they did, right? So this is ideal, and this is the non-ideal part, right? So they have two parts. Right. And but then you have a problem like we were going, so originally we took r squared times this and then integrated it, right? And then we figured out a way to integrate our x squared times exponential of minus x squared. There's a way to do that that I showed you that DiMarzio came up with, right? So we could integrate that, but you can't integrate this thing. There's no possibility to integrate this equation. There's no one's figured it out yet, right? So what you can do is do the derivative of that. So we did before, if you plotted r squared probability, you ended up with a peak. Then the integral part gave you like something out away from the peak, and then you take the derivative and find the actual peak value, right? So Floyd-Krigbaum figured out that you could take the derivative to get the coil size from that, and that's what they did. They took that function r squared times that, they did the derivative, and then you can get this expression, which gives you an expanded coil scaling. So I'll go through this next time, like on Monday, I guess, after I'll find some paper, but basically, so that's kind of the overview of it, like how it works. And I'll go through that again to kind of show you a little bit better how that works. But so you end up with a larger coil. Instead of n to the 1/2, it's n to the 3/5, which makes it, if n is a big number, that makes a significant difference. Right. So I'm out of time. So right. Thanks. See you on Friday. There's something coming in.